if we combine non-stationary variables together, almost always any linear combination of those non-stationary variables will be itself non-stationary. So for example, suppose we were interested in conducting some kind of regression but where the variables were non-stationary. It might be of interest to us to consider what would be the degree of non-stationarity or the order of integration of the residuals from that model. So suppose that we estimated the model yt equals beta 1 plus beta 2 x2t plus beta 3 x3t plus ut. Suppose also that all of these original variables in our model, that is yt, x2t and x3t, were all I1 variables. In other words, suppose they all contained one unit root. We can think of the residuals from any model that we estimate as being a linear combination of the original variables. So we could construct u hat t, which is obviously yt minus y hat t, which is going to be yt minus beta 1 hat minus beta 2 hat x2t minus beta 3 hat x3t. Well, obviously we know that y is I1, x2 is I1 and x3 is I1. What would be the order of integration of those residuals? Well, in general, we could show, and we could test it if we wanted to, that the order of integration of those residuals will also be I1. More specifically, if we formed a linear combination of variables where the highest order of integration of the component variables was d, then the linear combinations of those variables will also have an order of integration of d. In other words, the order of integration of any linear combination of variables will be equal to the highest order of integration of any of the component variables. Now that's almost always the case in practice. And it wouldn't matter what linear combination of the variables we took. In other words, if instead of taking beta 1 hat, beta 2 hat and beta 3 hat from an estimated regression, if we took any other values and stuck them in there, so we formed a different linear combination of these variables, that linear combination would still be I1. But there is a very special set of circumstances where if we take a set of non-stationary variables and form a linear combination, that linear combination will be I0. In other words, there'll be a special set of circumstances that may exist sometime where a linear combination of non-stationary variables is itself stationary. Now, as I said, this will be kind of the exception in practice rather than the rule, but there are some sets of circumstances where this will be the case. So we start off with non-stationary variables, we take the appropriate linear combination, and you can see here we are taking a linear combination of these variables, and that linear combination, instead of being I1, in fact will be I0. In other words, it will be a stationary variable. And the circumstance under which that would be the case is if the variables are co-integrated. Now, co-integration in econometrics is the way that we kind of measure and allow for the possibility of long-run relationships between variables. So, generally, if we combine non-stationary variables together, the combination will also be non-stationary. But under special sets of circumstances, i.e. if the variables are co-integrated, then combining together non-stationary variables results in a stationary linear combination. Now the idea of co-integration is that it represents a kind of equilibrium relationship between variables. So co-integration is the way in econometrics that we measure and test for and apply equilibrium relationships between variables. The idea behind co-integration and the reason that we start off with non-stationary variables but the appropriate combination is stationary is that many series that are non-stationary are seen to kind of move together through time. In other words, there are forces at work, economic or financial forces, which mean that we would expect some long-run equilibrium relationship between a set of variables to actually hold in the long run. And we could think of a number of situations where this might be the case. And I'll give you three such examples now. The first one might be spot and futures. prices for some given commodity or given asset. Secondly, equity prices and dividends. And thirdly, exchange rates and the ratio of relative prices between the two countries that make up the exchange rate pairing. Now, there are many other examples that we could think of in economics and finance, but these are three of the most obvious ones in some ways. The thing that's common in all three of these cases is that, as I said, there are some kind of market forces that we would expect to be at work, which would mean that the series involved in each case would be expected to have a long run or equilibrium relationship that should hold in the long run. Even if that relationship was not to hold in the short run, we would expect forces to be at work which would force it to work in the long run. For example, spot and futures prices. Spot and futures prices are essentially prices of the same asset or commodity, but just with different delivery dates. Spot prices are the prices for immediate delivery, obviously, and futures prices are the prices for delivery at some date in the future. Equity prices and dividends, similarly, we might expect to hold a long-run relationship with one another. And the reason for that would be that if I buy some shares today and I were to hold them into the infinite future, then the only return that I would receive back would be the dividend. So we wouldn't expect equity prices and the values of dividends to be able to deviate from one another in the long run. If dividends continually fell and equity prices continually rose, that wouldn't really make very much sense intuitively, because that would mean that in some sense, we were overpaying given the return that we'll receive in the form of dividends into the future. Similarly, the ratio of relative prices and exchange rates, we might think there would be an equilibrium relationship between. And I believe that I've mentioned this before. In economics, this is sometimes called purchasing power parity theory. And the idea behind purchasing power parity is that a representative basket of goods and services should cost the same when converted into a common currency wherever in the world it's bought. The idea behind that theory or that notion is that if this weren't to hold, then in some senses the law of one price would be violated. If a basket of goods and services were cheaper in one country than another, what we could do is hire a big van, go to the country where the goods are cheaper and buy them, ship them to the country where they're more expensive, sell them, and then convert the money back to the original currency of the country where we bought the goods, and we'd have some money left over. In other words, in all three of these cases, it's the existence of kind of no arbitrage conditions, or the fact that the possibility of arbitrage in the short run should ensure that any profitable, riskless opportunities to make money will disappear in the long run. So in all three of these cases, there could be deviations between spot and futures prices, between equity prices and dividends, or between exchange rates and the ratios of relative prices in the short run, but in the long run we would expect some relationship to hold. Now, from an econometric point of view, that's saying that there should be a long-run relationship between these sets of variables is equivalent to saying that we would expect them to be co-integrated. Now, technically speaking, the reason that we might expect co-integration is that the absence of co-integration implies the absence of a long-run equilibrium relationship, and this implies that the series could wander apart from one another without bound in the long run. Now, for example, if we tested spot and futures prices, we'd almost certainly find that those two were examples of I1 variables. In other words, they're examples of non-stationary variables that are well described by random walk processes. But if they were described by separate random walk processes and there were no long-run relationships between them, that means they could wander apart from one another without bound in the long run. So we may, for example, be able to plot the spot price on the y-axis against time here, and maybe it does something like this, and we may plot the futures price at time t over time, and maybe that does something completely different like this. If there were no cointegration and no long-run equilibrium relationship, this would be a possibility. But clearly in practice this wouldn't make sense. It wouldn't make sense for spot prices to keep rising here while the futures prices were continually falling. Obviously, we could have spot prices rising and futures prices falling for a period of time, but we wouldn't expect that to continue indefinitely because it wouldn't make any sense. And we'd expect arbitrage to develop into the markets where, for example, we'd buy the good or the asset for future delivery and then we could sell it in the spot market. And then we might find the possibility for arbitrage there. So once again, we would expect cointegration to exist in the long run for many series in economics and finance that are of interest to us. So cointegration is the way in econometrics that we represent long-run relationships and that we can get linear combinations of non-stationary variables that are themselves stationary. So how do we actually test for cointegration and how do we actually model variables that we think might be cointegrated? Well, the answer is that what we do is to form something known as an equilibrium correction or error correction model. Now, I think that these type of models, ECMs, are very, very clever. Because first of all they allow us to model non-stationary data in a valid way, and secondly they get around another problem which arose from the way that people used to deal with non-stationary data. Now, when the concept of non-stationarity was first considered by researchers in econometrics, the usual response was to separately take the first difference of each one of the I1 variables and then to run a regression on the first differences only. For example, if we started off with a regression model that related the variable yt to xt, but the problem is that y and x were I1 variables, we'd instead run a regression of delta yt on delta xt. Now that would work in the sense that obviously if yt and xt were I1 variables, delta yt and delta xt are stationary I0 variables. So that's in a sense a valid regression model. But the problem with such a regression model is that regression models containing only variables in first differences do not have a long-run equilibrium solution. So what this means is if we were to try and calculate the long-run equilibrium solution to the model delta yt equals beta delta xt plus ut, everything would collapse. Because in long-run equilibrium we set the disturbances equal to their expected values of 0. Delta yt and delta xt are also both 0. Because in long-run equilibrium the values of the variables are no longer changing. So we end up with 0 equals 0. In other words, such an equation cannot entertain or allow us to get an idea of possible equilibrium or long-run relationships between variables. So the particular feature of error correction models that's very appealing in practice is that first of all they allow us to model non-stationary data in a valid way, and secondly they allow us to get an idea of possible long-run equilibrium relationships that may exist between the variables. And that's something that's very important to us in economics and finance because we believe that these long-run or equilibrium relationships probably exist in practice. So if we have a look at the error correction model for a simple bivariate case where we've just got two variables y and x in our system, if you like, then this is an example of what the error correction model might look like. The way that we interpret the error correction model is to say that the error correction model contains two components. The dependent variable in the error correction model is delta yt, or the first difference of yt between time t minus 1 and t, the change in y between time t minus 1 and t, and that's explained by two separate things. First of all, the first differences of all of the explanatory variables, and obviously in the context of a bivariate set of data, we've only got one explanatory variable, and also a term which in parentheses here is known as the error correction or equilibrium correction term. Now, if we looked at this equation here and we were to ask ourselves the question, what is the long run or equilibrium solution to that equation? We would see that the long run or equilibrium solution is in fact given by what's in parentheses. Now, if we were to calculate the equilibrium solution, obviously ut would disappear, delta yt and delta xt would both disappear. Then we'd be left with beta 2 multiplied by yt minus 1 minus gamma xt minus 1 equals 0 as being halfway towards calculating the long run solution. We could then cancel out beta 2 and remove the time subscripts so that the equilibrium solution to that model would be, let me just create a bit of space on the board here, the long run or equilibrium solution to that model would simply be y equals gamma x. So that would be the long run or equilibrium solution to that model. Obviously, if we wanted to, we could add an intercept in here, or if our original regression model that we were interested in contained a number of variables, then the size of this long-run equilibrium relationship would correspondingly increase, so we'd end up with something a bit like this. So in the error correction model, the error correction or equilibrium correction term is the thing in parentheses. One of the other really nice features of the error correction model is that it has a really nice intuitive interpretation. The way to interpret the model is to say, why does y change between time t minus 1 and time t? Answer, it changes because some variable that affects yt, called xt, also changes between time t minus 1 and time t. And the impact of changes in x on changes in y are measured by the parameter beta 1. So we can think of beta 1 as measuring the short run relationship between delta yt and delta xt. And yt also changes between time t minus 1 and time t in order to correct for any disequilibrium that existed at time t minus 1. And the disequilibrium that exists is measured by this thing in parentheses. So we notice that the item in parentheses is measured with a 1-period lag. And as I said previously, that makes sense as well because we know that it wouldn't make sense for the current difference between yt and gamma xt to influence the change in y between time t minus 1 and t, because that would be like saying y changes between t minus 1 and t in response to something that's only happening at time t. In other words, something is changing today in response to something that's going to happen tomorrow. Clearly that wouldn't make any sense. The relationship in parentheses is the long run or equilibrium relationship, and we can interpret beta 2 as being what we might call the speed of adjustment parameter. That is, beta 2 measures how quickly delta yt adjusts or adapts in response to a disequilibrium in the previous period. Obviously, if beta 2 is large in absolute value, that means a relatively quick adjustment to a disequilibrium. If beta 2 is small in absolute value, on the other hand, that means a relatively slow adjustment back towards equilibrium. So, as I stated before, equilibrium, in a sense, is a theoretical construct, and a set of variables may never ever actually be in equilibrium. But the existence of this error correction term in the equation correctly suggests that there will always be forces that are kind of pushing the variables back towards equilibrium all the time, but there might be other forces which work against that at the same time, and those might be embodied by the delta xt term, which are pushing the system away from equilibrium. So we've got these kind of two competing forces at the same time. The equilibrium forces, which are forcing the variables back towards their long-run relationship, and these perturbations which might be measured by the changes in the explanatory variables or by the disturbances, which might be forcing the system or the set of variables away from equilibrium at the same time. So we have something known as the Granger representation theorem, which essentially suggests that any cointegrating relationship can be nested within an error correction formulation. So whenever there is cointegration, we can estimate an error correction model. So how do we actually test for whether a set of variables are cointegrated or not? Well, essentially, in order to test for cointegration, we estimate the potentially cointegrating regression and we check the residuals for whether they're stationary or non-stationary variables. So suppose that this equation up here on the board was the potentially cointegrating regression. So in other words, suppose that we thought the variables yt, x2t and x3t were the variables that may be cointegrated. How would we test for whether they're actually cointegrated in practice or not? Well, the answer is we would estimate this potentially cointegrating regression. We would collect the regression residuals, u hat t over here, and then we would test those u hat t to see whether they were stationary or not. So we would run the regression. For example, delta u hat t would be regressed on the lag of u hat t, and we've got some other disturbance term in this test regression which we might call Vt, which we assume has the same properties that we always assume of the disturbance term. And we'd run this test regression. We'd have as the null hypothesis that the value of C is 0 again against a one-sided alternative that it's less than 0. Now we need to think now about what our interpretation of the result would be if we either did not reject or we rejected this null hypothesis. If we didn't reject the null hypothesis, in other words, if we could not reject this null hypothesis, we could say under the null hypothesis, we've got non-stationarity in the residuals of the test regression. In other words, we've taken a set of I1 variables, we've looked at the order of integration of the residuals and found that those residuals are I1 if we don't reject the null hypothesis. Therefore, we've not found a linear combination of the variables which is stationary, because if we had, this would have been I0. So we've not found a set of a linear combination of the variables that is stationary. Therefore, under the null hypothesis, we have no cointegration. So under the null hypothesis, if we don't reject this null hypothesis, when we're testing on the residuals from the potentially cointegrating regression, we conclude that there was no cointegration. If, on the other hand, we tested these residuals and found we rejected the null hypothesis, that would mean that we'd found evidence against there being a unit root in those residuals. In other words, we would be concluding that in fact those residuals were I0. In other words, they were stationary. So that would mean that we'd taken a set of non-stationary variables and we found an appropriate linear combination of those non-stationary variables that were stationary. And that's exactly what cointegration is. So we could say under the alternative hypothesis here, we've got cointegration between the variables. So if we found cointegration, that means we found an appropriate linear combination of the original variables which is stationary. Now, an obvious question to ask is, well, how do we know that if there's a combination of the variables that's stationary, that estimating this kind of regression will find it? Well, it turns out, fortunately for us, that if there is any combination of these non-stationary variables that is stationary, then the testing approach that we've developed here will ensure that we find it. So if there is a combination of non-stationary variables that's stationary, we will find it by estimating this test regression. There cannot exist the possibility that if these residuals were I1, we could have found some other linear combination of the random variables that was stationary. That's impossible in practice. If there is a stationary linear combination of these variables out there, then running this test regression will find it. So what do we do if we either don't reject or we reject the null hypothesis in these two cases from a kind of practical model building point of view? Well, if there's no cointegration, obviously what that means is that there is no error correction model formulation. And you might say, well, if there's no error correction model formulation, what do we do? Well, the answer is the appropriate response then from a model building point of view is to estimate a model only in first differences. You might then say, well, we discovered previously that models only in first differences don't have any long-run or equilibrium solution. Well, that's certainly true, but obviously if there's no co-integration, then there is no long-run or equilibrium solution anyway. So the fact that we don't have any equilibrium solution to our model doesn't matter because there isn't any equilibrium. So if we find no co-integration between the variables, but the original variables were non-stationary, the appropriate model to build would be a model on first differences of all of the original variables. If, on the other hand, we find co-integration between the variables, then obviously if we just estimated the model in first differences, we'd lose all of these long-run properties that we're interested in. So the appropriate response to a finding of co-integration is to go ahead and estimate the error correction model. And that will enable us to validly combine the non-stationary variables and to get an idea of the long-run equilibrium solution. Now, it turns out that when we apply the Dickey-Fuller or augmented Dickey-Fuller or Phillips-Perron test to the residuals from this estimated regression, as we have done here, then we conduct the test in exactly the same way as we would have done if we'd been testing the original data y or the x's. The only thing that's different is the critical values. Now, the critical values, when we apply the test to the residuals of an estimated model, once again become larger in absolute terms than they were previously if we were applying the test to raw data. The reason that the values become larger in absolute terms than previously, in other words, they become bigger and more negative, is because we are estimating a model here, and to the extent that we estimate the parameters of this model wrongly, we'll have what we might call measurement error in these residuals, which then become the dependent variable and independent variable for the test regression. So the fact that we could perform an estimation here that might have some error in it, and the fact that we're now using residuals rather than actual data increases the amount of uncertainty associated with using the test. So that being the case, our critical values need to be bigger in absolute terms so that we need more evidence against the null hypothesis before we'd actually reject it. Everything else about the way that we perform the test is the same. Because Angle and Granger first suggested testing the residuals of the potentially co-integrating regression for non-stationarity in order to decide whether there's co-integration or not, because this was first done by Angle and Granger, an application of the Dickey-Fuller test to the residuals from a potentially co-integrating regression is known usually as an Angle Granger test. And as I said, we need to look up a different set of critical values. So how do we actually go about estimating an error correction type model? Well, there are at least three approaches that we could use. The first of these is known as the Angle Granger two-step approach. Another approach is due to Angle and Yu, and a final approach is due to Johansen. Now, the Angle and Granger approach is very, very simple, and although it might not look simple when you first see it, in fact, it's much simpler than the alternatives that exist. And that meant that it very quickly caught on, and it's still very widely used today. The Angle and Yu procedure is slightly more complex than the Angle and Granger approach, and is slightly more useful in some ways and gets around one of the problems of Angle Granger, but Angle and Yu never really caught on as a procedure because at the same time as the Angle and Yu procedure was being developed, an alternative and arguably much more general and far superior approach due to Johansen was also developed. So the Angle Granger approach and the Johansen approaches are by far the most common approaches actually being used today. We'll only look at the Angle Granger approach on this course. The Johansen approach is beyond the scope of this course, but there's quite a bit of detail on it in my book. And for people who do financial econometrics as a course later on, then we discuss the Johansen technique there. But coming back to the Angle Granger technique, how is that actually performed in practice? Well, the first step is to ensure that all of the individual variables that we think may be co-integrated are actually non-stationary. Obviously, if any of these original variables were already stationary, it wouldn't really make any sense to include them in a co-integrating regression. Because obviously the idea of co-integration is that we start off with non-stationary variables, and when we link them together in the appropriate linear combination, they become stationary. If one or more of the variables was already stationary, clearly that wouldn't make any sense. So the first step in the Angle Granger approach, or rather the first part of the first step, is to ensure that all of the original variables are I1. The second step is to actually estimate the potentially co-integrating regression here, collect the residuals, and then test those residuals to ensure that those residuals are stationary. So we'd estimate this regression, get the residuals. If the residuals are stationary, therefore we've got co-integration, we can proceed to the second step of the estimation procedure. If we don't reject this null hypothesis and we conclude that the residuals from this potentially co-integrating regression are non-stationary still, then clearly that wasn't a co-integrating regression after all, and we have to form the model in first differences only. If we have found co-integration, however, then we can go ahead to conduct the second step of the Angle Granger approach, and that is to use the residuals from the first stage regression as the error correction term in the second equation. So you can see we can replace the lagged value of the residual, which is obviously this thing over here. We can use that to replace the equation as I put it previously as the error correction term in the equation. So the variable that we actually use is the lag of this residual here, which is obviously exactly equal to the lag of this thing over here. So we can then estimate the error correction model in the second step, and the beauty of the error correction model is that all we needed to do essentially was a set of ordinary least squares regressions. In fact, we estimated, apart from the unit root testing part, we estimated two separate ordinary least squares regressions. The first of those regressions was to estimate the potentially co-integrating regression using ordinary least squares. Secondly, we estimated the error correction model again using ordinary least squares. So therefore, we don't need any more complex or technical estimation procedures than we've already developed on this course. So that's another really neat feature of the Angle Granger approach to testing for co-integration. Now, as with many other situations in econometrics, whilst the Angle Granger approach is a very useful one and a very widely used one, it suffers from a number of problems in practice. And these are the ones that kind of led to the development of the Johansson procedure and mean that Johansson is perhaps on balance more widely used now than Angle Granger. The first of these comes back to this problem that unit root tests have low power in finite samples. Now, I said previously that one implication of unit root tests having low power is that we might have a tendency to conclude that series have a unit root when in fact they don't, that is, they're stationary. Equally, if we are applying unit root tests in the context of a potentially co-integrating regression, then the problem of low power in finite samples will mean that we'd be prone not to reject this null hypothesis sometimes when we should have done. In other words, in some situations in practice where there is co-integration between variables, we might be inclined to not actually find that co-integration. The second problem that exists in practice is that the Angle Granger approach forces us to treat the variables in our set of variables asymmetrically from one another. In other words, when we move away from the setup that we had before in this course, where we knew what the dependent variable is, that's the variable whose movements we're trying to explain, and we knew what the independent variables were, they're the variables that are doing the explaining. When we move away from that situation to the concept of possible long-run equilibrium, we might not really have any idea from theory which of the variables we should call y and which of the variables we should call the x's. In other words, for example, if we're interested in estimating an error correction model for spot and futures data, then it may not necessarily be clear to us which of either spot prices or futures prices we should call Y and which of those we should call X. So if we don't know which we should call Y and which we should call X, then what we'd like to do is to have a framework that allowed us to not have to make that distinction. But unfortunately, with the Angle Granger approach, in the first stage we have to estimate the potentially co-integrating regression, and that forces us to say one of the variables is called Y and the others are called X's. The final problem is that we cannot perform any hypothesis tests about the actual co-integrating regression. So if we look once again at our error correction model, we know that we can perform hypotheses validly about the values of the beta coefficients because delta yt, delta xt and the term in parentheses taken together are stationary provided that the variables are co-integrated. So we can perfectly validly test hypotheses about the betas, but we cannot test any hypotheses about the values of the parameters in the potentially co-integrating regression. So we cannot test any hypotheses about the value of the gamma parameter I put up in a previous slide. And that's unfortunate in many ways because there might be situations where we're actually interested in testing hypotheses about the value of gamma. Now, the first of these three problems, that is that unit root and co-integration tests have low power and finite samples, is a problem that disappears asymptotically. That is, as we increase the size of the sample, the problem of the lack of power will gradually disappear. In other words, the power of the unit root and co-integration tests, the power of the Dickey-Fuller and Phillips-Perron tests will increase as the sample size increases. So that's not really a big problem. The third of these problems, that we can't perform any hypothesis tests about the actual co-integrating relationship, is overcome by the Angle and U approach. But as I said before, there is an arguably much better approach which meant that Angle and U is not actually used very much in practice. And that better approach, which gets around both the problem of Angle Granger forcing us to treat the variables asymmetrically and the problem that we cannot perform hypothesis tests about the actual co-integrating relationship, is the Johansen approach. So for those reasons, arguably, Johansen is by far the superior approach. Although, as I said, the reason that we don't look at it on this course is that, unfortunately, it's inherently very much more complex. It's very much more complex to actually calculate the test statistics, and it's very much more complex to kind of intuitively understand what's going on with those test statistics. Angle Granger, whilst it's flawed, it's very nice and simple, and that's one of its biggest advantages.